Så med det tror jeg skal gi ordet til Jan Petter.
Takk, Helge. Takk. Og siden vi bare har en halvtime, så får jeg gå rett i gang. Da dette første innlegget er først og fremst knyttet til bærekraft og den problemstillingen som står under. For det er noe som har opptatt meg i relativt lang tid. Og spesielt gjennom et arbeid og et kurs og litt sånt som jeg holder på med på Norges handelshøyskole. Så spørsmålet er altså i hvilken grad kan vi klare oss 100% på fornybar energi. Og da unntatt kjernekraft. Det er spørsmålet, og det skal jeg nå gå i gang med. Her er et par eksempler på hvorfor jeg synes dette er et viktig spørsmål å ta opp utifra et passionsløst vitenskapelig synspunkt. Fordi at både i den vitenskapelige litteraturen, det er et eksempel her, og selvfølgelig i ulike interesseforeninger for ulike energikilder, så fremkommer det, eller så står det veldig ofte skrevet av at selvsagt kan vi klare oss med fornybar energi og her på denne planeten. Og i Norge så har vi flere miljøbevegelser som er veldig tydelige på dette. For 10 år siden så skrev Marius Holm i en kommentar til noe jeg skrev, der han startet med at jeg ikke visste forskjell på fart og akselerasjon, at 10 år senere så ville solenergien være den dominerende energikilden her på jorden, og fortrenge faktisk all fossil kraft omkring 2040. Så nå har det gått noen år, så kan vi kikke tilbake igjen og se på hvordan situasjonen ser ut. Og dette som skulle fortrenge all fossil kraft, det er dette grønne sammen med det, kanskje sammen med det blå da. Men det er liksom det som er resultatet. Velkommen. Per i dag. Og som vi ser det, så domineres verden fremdeles av kull, olje og gass. Det var litt merkelige farger der, så det var ikke de samme fargene der så her, men summen av oljen skimtes der. Så andelen av fornybar energi er ikke stort annerledes i dag enn den var faktisk for 20-30 år siden. Og verden fremover, tiden fremover, den er slik at for det første, sånn at den røde linje her, den viser liksom folketallet, så den jordens befolkning, sånn at det er en ganske tydelig 99,92% korrelasjon mellom befolkning og energiforbruk på jorden. Og vi er kommet rundt her, og da står vi også foran en situasjon hvor verden skal bli opp mot 10 milliarder mennesker innen 2050, og kanskje enda flere utover mot slutten av århundret, hvor man kan tro og håpe på at jordens befolkning stabiliserer seg. Så det er på en måte ståa i dag, og jeg synes at jeg skal vise nå at dette her er det ikke mange som, altså, når man ser på forskjellige outlook og scenarier rundt omkring, så synes jeg det perspektivet mangler veldig mye. Men jeg tror det jo jeg hadde 1 til 2 timer for meg selv her, sånn at derfor så hadde jeg tenkt å begynne med 2 enkle ting her. Det er 2 gamle lyspærer som akkurat er 100 watt. Og hvorfor skrev jeg de opp? Jo, fordi at 100 watt, det er faktisk den effekten som vi går på alle sammen. Og det det sier noe om hvor fantastisk effektiv vi blitt som etter 4 milliarder år her, eller vi alle blitt. Og det synes jeg var et perspektiv som manglet på Darwin-dagen i går. Og i det jeg skulle stille spørsmål om det, så fikk jeg beskjed fra min sønn at nå kjørte han hvis jeg ikke kom ut. Så jeg kan ta det senere. Så vi trenger bare 100 watt. Men hvis vi ser på denne totale effekten for hele jorden og deler på da antall mennesker, så får vi 2,4 kilowatt. Og det er da et par kokeplater sånn som dette. Det er det hver og en av oss krever for å ta del i den humane sivilisasjonen. Hvis vi ser på hvordan dette er fordelt på ulike land, da, så har vi, her har vi Europa, det er denne grønne linjen her, så ser man at faktisk så har effekten per person gått litt grann ned, men stort sett så kan vi si at den er relativt stabil rundt 4 kilowatt per person, kanskje litt over. Og verden, jorden som helhet, den ligger her på 2,4 watt nå. Vi ser det har gått litt opp. Hvorfor har det gått opp? Jo, det er først og fremst på grunn av Kina som har hatt en voldsom industrialisering, og nå nærmer seg Europa i energiforbruk per person. Og så ser vi da lenger nede på listen, så ser vi Latinamerika, India og Afrika som ligger her nede på begredelig under 1 og ca. 1 kilowatt per person. Og det som utgangspunkt eller premissen for det som kommer senere, det kan man jo også være enig eller uenig i, men jeg oppfatter, jeg anser livet i Europa som relativt stabilt, et bra liv, og noe i nærheten, om alle mennesker på jorden kunne levd på dette nivået, ja, så kunne vi hatt et bra liv på jorden, og samtidig hatt ikke problemer med ulike ting som flukt, migrasjon og kamp om ressurser og så videre. Sånn at hvis man svelger den premissen der, så betyr bærekraft at 4 kilowatt per person globalt i 2050, det er 50 terawatt til sammen. Mot det vi ligger på i dag, ca. 19 terawatt. Og hvis vi da ser på kanskje den mest kjente organisasjonen sitt fremtidsscenario, så ser vi for eksempel International Energy Agency. Hvis vi ser på status i dag, og så ser vi på ulike business as usual og helt fornybar eller 1,5 grader scenario på ene siden, og nærmest hvordan det går med rett fremstilling, så ser vi at det er ingen økning i total energi. Og det var det jeg prøvde å si at jeg er veldig kritisk til i begynnelsen. For uansett hvilke disse scenariene er riktige, så fortsetter verden i faktisk større energifattigdom enn den er i dag. Og så kan man si, hvorfor ikke heller minke, hvorfor ikke senke energinivået per person, sånn at vi i Europa skal ikke lenger gå på 4 kilowatt, eller vi i Norge skal ikke lenger gå på 6-7, som vi vil gå på hvis vi tar bort den tunge industrien, nedlegger kraftkrevende industri. Ja, det innebærer konsekvenser, og de konsekvensene er kanskje ikke så lett å ta inn over seg. Her er en som snakket høyt og tydelig om behovet for et grønt skifte og ta inn over seg den klimautfordringen som vi står i. Men når han ble intervjuet om han kunne tenke seg å avslutte, ikke reise på ferie til Barbados, så var det ikke så interessant. Og det er jo faktisk sånne ting man er nødt til å lage en lang liste over hvis vi vil gå fra 4 til 3 kilowatt per person. Og så kan man si, hvorfor i himmels navn skulle man gå til 3 kilowatt per person når 4, og for den saks skyld 5 eller 6 kilowatt utrolig lite i forhold til den totale bedriften, eller den totale energiomforvandlingen per tid som foregår på jorden, som da drevet av solen med 174 000 terawatt. Og det klart at om vi bare hadde hatt en fornybar, hatt en rimelig ren energiproduksjon her på jorden, så hadde dette vært en helt ubetydelig del av, hva skal vi si, den biologiske livet på jorden. Så jeg går tilbake til det at denne premissen om at 4 kilowatt er et realistisk mål, og drømmer om å ligge her nede på 2, under 2 for eksempel. Da er vi på en levestandard som ikke i nærheten av det vi kjenner i Europa, og det tror jeg ingen ønsker egentlig, heller ikke de som ikke bor i Europa. Så det var innledningen, og så kommer vi til selve regnestykket. Så det er bare et enkelt regnestykke jeg har her i dag. Så hvis vi da skal leve av fornybar energi, så utfordringen, det som er den egentlige utfordringen, kanskje den eneste utfordringen, vil jeg si. Ja, det finnes andre også. Men det er jo da energiintensiteten på de ulike kildene her. Sånn at hvis vi ser for eksempel på vindkraft, så ser rundt omkring på hva vindkraft egentlig produserer, selv om det blåser kanskje 10 meter per sekund i gjennomsnitt mange steder. På gode vindsteder så leverer de fleste vindkraftverk i størrelsesorden 2 til 4 watt per kvadratmeter. Solceller kanskje 5 i Europa og 10 i Sahara. Mens planter, det er liksom nede på 0,5 watt per kvadratmeter. Vannkraft i Skottland, det er jo mindre effektivt enn i Norge, sant? Men det er liksom dette i forhold til fossil energi, som er enkelt å få fatt i og koster lite, som da er en faktor 100 eller 1000 mer. Og så har vi kjernekraft som er en faktor 2, 3 eller 5 eller 10 mer intens enn fossil energi. Men nå skal jeg bare vise hva som skjer hvis vi da begrenser oss til de tingene der. Men aller først så vil jeg bare peke på at det ikke er tall som kommer rett ut av luften. Her er da en sånn her statistikkside i England for eksempel, som viser da hvordan offshore vind produserer til enhver tid. Så dette var en dag, det blåste i hvert fall mye her i Norge, men hvis vi ser på Hywind Skottland, så er det nede i 1 watt per kvadratmeter på det anlegget den dagen. Og så går det da, de som hadde de beste forholdene den dagen, ligger opp på 5,5. I går så produserte Hywind på 4,0 watt per kvadratmeter. Hvis vi ser på solenergi, litt eldre bilde, men de fleste områdene i Europa ligger på 5 watt per kvadratmeter, og så kommer det opp i mer lukrative solenergiområder, da kan vi komme opp i rundt 10 watt. Hvis vi ser på her et eksempel, da, Benban Solar Park i Egypt, den ble åpnet i 2019, og leverer da enn så lenge 11 watt per kvadratmeter. Slik at sånn kunne man fortsatt å snakket om dette, men de tallene de står for seg selv. Og skal vi da, så er det liksom, hvor ender dette? Altså, hvis vi tenker oss et helt sånn hypotetisk globalt energisystem, så holder de gjerne med, så trenger vi faktisk ikke å tenke på lager, energilager og dette med intermittency. Fordi at i så fall så hadde det alltid vært sol noen steder. Det har alltid vært vind noen steder, og egentlig så hadde det vært stabil energiforsyning. Men hvis vi nå tar lærdom av hva som har skjedd i Ukraina, så det klart at hvis hvert land sørger for sin egen energisikkerhet og energiproduksjon, så har man en helt annen, så slipper man å være avhengig av land som man spesielt nå ikke lenger vil være avhengig av. Og det krever da energilager til typisk 100, kanskje mer dager, som vi må ha i tillegg når sol og vind ikke blåser. Og så har vi også det at hvis vi skal lage hydrogen, ammoniakk eller andre flytende drivstoff, så trenger vi også mer energi enn bare til primærbehovet. Så la oss nå si at gå ned til 2 watt per kvadratmeter som da tar hensyn til lagerbehovet, og så ergo så trenger vi 2000 kvadratmeter hver og en av oss for å forsyne for nok energi. Og det gir da 20 milliarder kvadratkilometer av jordens overflate som må brukes til energiproduksjon. Og det noe problem? Vel, da får vi se på jordens overflate. Her jordens overflate viser seg å være det som bobart, minus isbreer og litt andre ting. Det drøye 100 millioner kvadratkilometer, sånn at i forhold til 100 så kanskje ikke 20 så mye. Vår klimaminister allerede fredet 30% av det. Der skal dyrene få gå i fred i skogen, og det skal være urørt. Dermed så ble jordens overflate tilgjengelig for menneskelig aktivitet 30% mindre. Og på dette da, så skal vi da legge inn 20 millioner kvadratkilometer til energiproduksjon. Og da ser vi at det ble ikke så mye igjen til jordbruk hvis energiproduksjon utelukkende fortrenger jordbruket. Det trenger det selvfølgelig ikke være, men vi ser at dette her en stor del av det som tilgjengelig. Men det var hele jorden. Hvis vi nå ser på at kanskje skulle det være sånn at regioner og store land og sånt, de må være selvforsynt energi. Så at hvis vi nå bruker det, hvis vi ser på folketettheten og deler den på 4 kilowatt, så får vi da prosent av landet eller regionen som må brukes til energiproduksjon. Og vi ser at i Europa så folketettheten ca. drøyt 30 personer per kvadratkilometer, og det betyr at 13% av overflaten til Europa må brukes i dag. Selvfølgelig kan vi ta litt havflate også, men størrelsesorden der. Hvis vi tar vekk 30%, så går det opp i 19%. Ja, kanskje mulig, tenker noen, men for de områdene hvor det store, helt andre befolkningstettheter, Kina, India er allerede over 100% av landets overflate til energiproduksjon, om man skal fylle opp med sol og vind og de andre tingene til 2 kilowatt. Og Afrika, som på vei til hvor det blir voldsom befolkningsvekst fremover, det kommer opp i 47%. Sånn at ting ikke enkelt, og selv med 13% eller 10% dekning av arealet, så vil mange steder se sånn som dette ut, og spesielt i Norge så dette siste ikke veldig populært. Og fremdeles så ser vi da at for eksempel i India så skrives det rapporter og papir om hvordan 100% av India kan forsynes med fornybar energi med vind og sol og jippi, og så kommer man gjennom. Og det er på en måte et stort dilemma, tenker jeg. Her er en Fraunhofer-rapport som hevder at det er mer enn nok land i Tyskland, fordi at jordbruksarealet kan brukes dobbelt. Men det må jo være sånn at hvis du har solceller på jordbruksareal, så vil jo solcellene absorbere mesteparten av sollyset. Og det vil i hvert fall redusere effekten på jordbruket kolossalt. Pluss at du må lage veldig små eller andre traktorer og sånne ting. Sånn at dette stemmer liksom. Når jeg ser på sånne ting, så reagerer jeg på det som fysiker. Selv om jeg i utgangspunktet er veldig også glad i vindkraft her i Norge. Sånn at siden jeg bare fikk en halvtime, så skal jeg begynne å avslutte. Sant? Jeg tror at faktisk hvis man skal være realistisk, så er mer enn 10% av et beboelig landområde i et land eller en region urealistisk. For det kunne vært realistisk hvis alle, for eksempel en kompis og kollega av meg som bor i Paris, han mener det at livet utenfor den indre sirkel i Paris, det er ikke verdt å leve, sånn at alle skal være der. Og da kan vi selvfølgelig gjøre noe sånt, men slik er det ikke mulig i praksis i virkelig land. Andelen fornybar energi i verden er kanskje der omkring, sånn at hvis vi da ser på, dette var mitt anslag, og hvis jeg ser på hva IEA sier om situasjonen i 2050, så vil, avhengig av hvilket scenario det er, så er det 5-8 terawatt fornybar energi som leveres i 2050. Og det er jo fantastisk bra, men det er likevel fantastisk dårlige nyheter, fordi at energibehovet er så mye større i 2050 enn det nå, og 5-8 terawatt, det er ikke engang halvparten, det er under halvparten av det som er energiproduksjon i dag. Sånn at en annen energiform må stå for minst dobbelt så mye, kanskje 15-25 terawatt. Det står det ikke i A sin outlook, det står det bare her. Og den energiformen er ganske innlysende for meg at det er dette som er den eneste løsningen. Og det tenker jeg kan være en avslutning nå, siden det ikke var mer tid, for jeg har et lite kapittel om situasjonen i Norge, men det kan jeg eventuelt ta en annen gang hvis noen har lyst til å høre på det. Så takk for oppmerksomheten.
As he said, my name is Niels Berger. I'm Swedish. My father was Norwegian, mother Danish. So I was actually a Norwegian citizen until 2008, and then I became Swedish after that. I'm from the insurance business. I did insurances for ships and energy insurance. I did Statfjords, the first tow out to the field. I did Sleipner, the one that turned over. I was the broker for. And in 1991, I moved to Miami and became an insurance broker in the United States. And I was handling South America and the Caribbean. And got a job with my client who ran large tankers in the Bahamas. And those tanker owners, that's the basis of ThorCon. We realized that we have an energy problem in the world. We have too many people that are living below poverty level, and all the people below poverty level wants to rise above and have a decent life. And we were shipping oil, so we weren't helping. We were taking crude oil from the Middle East to the US and to China, Japan, etc. But our founder, Jack Devaney, who is a professor from MIT, he sat down and realized that we need something else. And he quickly came to the conclusion that nuclear is the solution. This is our vision of our first plant. I'm going to come back to that one later. But So this is where we come from. Jack, he built the last 4 ULCC tankers, which are almost 400 meters long, built them in Korea, and quickly came up with the idea that, if we can build nuclear plants at shipyards, then we are solving a lot of problem with delays, cost problems. And to the right, you can see a vision of our 1 gigawatt plant, and it's about 2/3 of the size of a ULCC. Those are old enough will remember seeing ULCCs in the fjords around here. Those who are not young enough, old enough, have no idea what it is. But there were, 20, 30, 50 of these lying in the fjords of Norway and Sweden back then. Building in shipyards obviously means that we can do quick construction, and we have the possibility to have economy of scale. When you build in a shipyard, there are usually 4 or 5 ships being built at the same time at different stages, and you just follow like the rolling lane, like when you build the Boeing airplanes. It's the most economical way of building. A picture of the DSME shipyard in South Korea. Once our plant is built, we will tow it, either, in this case, a wet tow, means it's floating, or on a heavy lift down to site. And there's a picture of the island, Kelasa Island, which is the island site that we've been given by the Indonesian government. A lot of people that we meet are very much afraid of nuclear. What happens if something goes wrong? The aircraft industry have 2 dominant players, Airbus and Boeing. Boeing has, for years, spent their business model on human training and having humans controlling the airplanes, whereas Airbus has the total opposite approach, whereby the technology runs the plane. And with ThorCon, we have adopted the Airbus approach. We do not let humans run our nuclear plants. They'll be run by the technology that we have developed. So what's our plan? We are going to build a test plant, non-fission test plant somewhere in Indonesia, which we estimate will be finished sometime in 2024. Then we will test it, and based on those tests, we will start the construction of our commercial reactor, which we expect to be on site in 2028. Tested and started producing electricity 2029. And then you can see how we are able to scale up in only a matter of years. We can have 18.5 gigawatt online with our technology. When we started talking to people, they would say, oh, nuclear is too expensive. There's no way we can afford nuclear. So we quickly realized that we have to be cheaper than coal. Otherwise, we cannot get countries in the third world to listen to us. Our production cost, our cost for the electricity is 3.5 cents per kilowatt hours, all in. Building, operating, decommissioning. In this example, we're showing what the price of coal, the electricity from coal is in Indonesia. It's 6.5 cents. So we found that the Indonesians could be willing to give us a power purchase agreement at the same price as coal, which means that one plant would generate 3 cents per kilowatt profit, which is $236 million per year per plant. So not only are we giving clean electricity to the third world, we're also offering very lucrative returns for the investors that we are seeking. It's just an example for, in our when we approach finance guys, where we have divided up the investment in different tranches, where you can see that over this period, your return will be 10 times what you put in, which is quite good. Why did we pick Indonesia as our test market for the technology? Well, it's the fourth most populous country in the world, 270 million people. There'll be 350 million in about 20 years' time. Half of the people live on Java. And if you've been to Indonesia, you've probably been, see to the right, been in traffic like that. That's traffic every day in Jakarta. It easily take you 3 hours to get from a hotel to a meeting, and it's not good. What we have done and what we're doing in Indonesia is that we set up an office there in 2016. We have 18 people working for us in Jakarta. We are working actively with the local departments, with their nuclear regulators, with their power company, and we are expecting that during 2023 we will have started terms of reference agreement with the nuclear regulators to get the basis for our technology licensed. We have support from the president, which is important. They have an election next year, so we're very keen to have many of the permits in place before the election, because you never know with elections. We have been given a demonstration site, which is on a island called Kelasa Island. If you look, you probably recognize where you are if you see the picture. It's halfway between Jakarta and Singapore, and not very inhabited. And there's a small island called Kelasa Island outside of Bangka Belitung, which you see on the right, and the big cove to the north on the island. That's the site that we have been given. And that's our vision of how the site will look once it's fully operational. With some accommodation units, not sure why we put in a tennis court, which is too hot to play tennis, but we did. That's the problem with designers. They put in something that you really don't need. The unit you see here is a 500 megawatts, so it's half the size of a full nuclear plant. But the test reactor we're building is 500 megawatts, so that will be the first one built. So we've developed a small modular molten salt reactor technology where we can provide the world with low-cost dispatchable power that's clean and safe, which is exactly what the previous speaker was looking for. We address all the problems that currently exist with the nuclear energy, which is it's over-regulated, it's always delayed, and it's overpriced. And Indonesia, they really have an ambition for a cleaner and more prosperous future. And we've done research in the various parts of Indonesia, and where there's a high percentage of the people that are pro-nuclear in Indonesia. They're realizing this is something that can give us the clean electricity we're looking for. Thank you.
Okay. My name is Lars Jorgensen. I'm the CEO of ThorCon US. We're doing the technical development for the reactor. A good place to start is to say, well, what are the priorities? If you have to do design trade-offs, what's more important than other things? So one is inherent safety. We really want the safety to be independent of the operators. Boeing learned a hard lesson by expanding rapidly into the developing world and having pilots that were less skilled than in the US. And so we had the 737 MAX incident. So we are taking the position that we want safety to be independent of any operator action. That includes both that they don't have to do anything in the case of an accident and that they can't do anything to cause an accident. We have a big advantage over the airline industry, though, in that airline industry has no easy way to be fully passively safe. I mean, they're up in the air, they got to land. For our case, all we have to do is shut down and keep it cool and keep things contained. We can also do that depending primarily on gravity, not electricity or complicated machinery or software. The other big issue with safety is public reaction. We've had 3 major accidents in the world with nuclear power. You probably can name them, but if you think about it, the older one, 3 Mile Island, is now about 50 years ago, was an industrial accident that didn't hurt anybody, and yet you can name it. It gives you an idea of just how much hype there is around accidents. And if you look at the accidents, the harm that has come to the public has been from poor public reaction, people doing panic evacuations and the like, including in Japan, the most recent one. So we plan to demonstrate accident conditions, even worse than Fukushima, to show that there is no reason to do a rapid evacuation. We have to be low cost. We have to be able to compete with coal and liquid natural gas in the developing world. They don't have as much electricity as they want because they can't afford it. As soon as they can afford something, that's what they'll buy. So we have to be able to compete head on in cost with coal. We view coal as our main competitor, not other nuclear companies. We are being privately funded, which means we have to keep the development time short, get to first critical in about 3.5 years, because people who invest money want to start getting return on their money as soon as possible. That means that we accept good enough nuclear rather than the very best. We are not trying to be a breeder. We're just trying to get a basic plant running. Once that's running, then we can work on fancier things. We want to be able to deploy rapidly. Nuclear plants typically take a decade or 2 from starting building before they're finished. There's a lot of political stuff that happens in the meantime, and that makes it so that there's actually a high risk of a nuclear plant being started and not being finished. So we're targeting being able to go 2 years from order to grid. That means once you've already got the permits and the land bought, which are the minor portions of investment, and then you start building, that we would be able to build in 1 year and get it on site and test it for 6 months or so, and then be able to start producing revenue. We want to be scalable. Building 1 or 2 or 4 gigawatts in a year just isn't going to make a difference in the world. It might be a nice investment financially, but if we're going to make a dent in the world, we really got to get at least to 10 gigawatts, maybe up to 100 gigawatts of new power plants every year. 10 gigawatts would be roughly the size of an Enron or one of the major oil companies. I used Enron, I meant Exxon. 100 gigawatts, I think, is roughly the total market size. Things that are not as important. Fuel economy. Nuclear fuel is around 0.5 cent to 0.6 cents per kilowatt hour. Yeah, you could go to a breeder and get that down to 0, but that's not the cost driver. So we want to keep things simple and not focus on fuel economy. The other is waste generation. If you do a breeder, you can get the waste generation down by at least a factor of 10. But as it is, just a normal plant, we're talking a little over 1 liter per person for their lifetime supply of energy. So the waste is not a huge issue in the first place. It's such a small volume that we can keep it well contained. Here's a picture of the design. I'm going to have to go faster. We build it like a ship. Here's the reactor itself, then a series of heat exchangers before you get to the turbine generator. And you see the turbine generator is a big portion of the whole thing. And then at the very end, you see the switch yard. In this case, we use gas insulated gear. And finally, the transmission lines going out. So we go from seawater coming in to electricity going out and everything in between. There's even accommodations for the crew so that we can be deployed either onshore or close to the shore, or even 5 or 10 or 15 kilometers away from the shore. These towers here are for removing the decay heat. We'll talk more about those in a little bit. They are not for removing the primary power producing heat. That's removed with once through cooling. Because we're going to a developing world, we're expecting an unstable grid, and we have to have the ability to both do black start and load follow. Given the molten salt temperatures, we're able to get just under 50% thermal efficiency as compared to most nuclear plants, which are in the low 30% range. Just to give you an idea of size, we're talking roughly 160 meters long by 33 meters high and 65 meters in the other direction. It is built like a ship. For those of you with some shipbuilding experience, you'll notice the double hull here with all the ribs and the webbing. It is designed by Jack Devaney, who was a naval architect instructor at MIT and then for the Navy, and built the largest oil tankers. So we have started from, we got to build it in a way that the shipyard is really comfortable so that they can build it rapidly, and we'll fit our pieces inside. Just to give you an idea of scale, this is a sketch of a typical coal plant. And to the same scale, here's a sketch of the heat producing portion of our power plant. Now, the turbine generator is going to be the same size for the two of them. But we argue that there's no reason we shouldn't be able to beat coal in cost. We're just a lot smaller. Here's a lot of detail on the loops. So we have one loop which goes from 560 to 704. That's a molten fluoride salt loop. The salt boils at about 1400. So we have a large margin between what our high operating temperature is and before you go from a liquid to a gas. That means we really don't have any serious way of developing any significant pressure. Get this to go away. There, that's better. So we pump that around into a secondary salt, which is chemically compatible with the fuel salt in case there's a leak. Then we pump that around to a solar salt. This gets its name from thermal concentrating solar power plants. It's a nitrate salt. It is quite compatible with steam. And since getting a leak in a steam generator is pretty common, we needed to be sure that this third loop was compatible with moisture. If you put moisture into this fluoride salts loops, you tend to get hydrofluoric acid as a gas, which is not nice. So we wanted that loop to keep them separate. The other thing this does is it keeps the high pressure from the steam generator isolated from the lower pressure systems here, where you're looking at like 7 bar. So very modest pressures. We can use standard stainless steel piping for these. We don't have to have exotic forgings. And then the power plant itself, the turbine is run-of-the-mill steam plant from a coal power plant. Similar conditions, it's supercritical single reheat. Here's a lot of detail on what the turbine generator side would look like. Overall, light water reactors are about 33% efficient. We're closer to just shy of 50. So we have about 1/2 the cooling requirement compared to a light water reactor. Another picture with all of the details. Mostly the emphasis I want to get out of this is a complete power plant. We can tow it to a site, and all you have to do is ballast it down so it sits on the seabed, hook up your cooling water. So we have to have inlet pipes dredged on a per site, and then hook up the transmission line. Everything else is already built in. That means we're doing all of the construction work at the shipyard, and we have a very firm schedule. Nuclear power plants tend to be very unsure of their schedule, anywhere from 10 to 20 years. We have experience building in the shipyards and normally get 1 year with build times with very sharp penalties if they are late in delivering. Looking inside, you have a pump that pushes the salt around. The hot salt goes through the heat exchanger and then down and goes up. This is the reactor itself. You'll notice it's shaped mostly like a sphere, and then it goes back up. So we call this the primary loop, where the salt flows around and stays inside that closed system. The green pipes are the secondary salt, so that the heat exchanger transfers the heat from the fuel salt to the secondary salt. One thing we do have to watch out for is that we're operating at 600 to 700 degrees C. That's a long ways away from room temperature. So there's a lot of thermal expansion that goes on, and you really need to be careful with how you arrange things and how you support them to be able to tolerate the motion that comes with the thermal expansion. A question we often get is, salt is really corrosive. And it's true that a mixture of salt and water is very corrosive, but pure salt is actually less corrosive than pure water at these temperatures. So the key is to make sure that the salt is pure. When we do that, the corrosion is less than 100 microns per year. So we can make the pipes just a little bit thicker and address the corrosion issue. So for safety, one of the things you have to do is to stop the fission process. That happens by physics by itself if the temperature rises. It's called a Doppler effect, but you can engineer the way that you've designed the core so that if things go over temperature, the fission is just going to stop all by itself. And that happens for us within about 20 or 30 degrees over our normal operating temperature. We do have that backed up by shutdown rods that can drop. They are held up by electromagnets, and if we sense that we're over temperature, you cut the power to electromagnets and the shutdown rods will drop by gravity. The second big thing you need to do is keep the radioactive particles contained. We have two gas tight barriers, and since we have such a big margin to boiling, we don't have any pressure wave to deal with on those gas tight barriers. So they're not challenged even in an accident. The last thing you need to do is to remove decay heat. That's actually the most challenging aspect of nuclear. After you stop fission, you still have about 6% power due to decay heat. In our case, that's 30 megawatts. You have to remove that or you get in trouble. And that was the problem both at 3 Mile Island and at Fukushima. So here's a picture of the primary loop inside this red thing, which we call the can. That's our first containment barrier. If anything overheats, then we stop cooling the freeze valve and the salt drains to these drain tanks. You'll notice the drain tanks are spread out rather than concentrated. So in the pot, we have the critical mass, but once we drain, we do not have a critical mass. Everything is spread out and it cannot be critical. And furthermore, it has a large surface area to volume ratio, so it has good cooling. So it can take the heat of the salt draining and take the full load of the decay heat. That heat gets transported by radiation to the cold wall, which is basically a wall of water. So we transfer by radiation heat to the water, and then that water will flow up by natural circulation. So it flows from the drain tank into this water. It goes up into an expansion tank and then to radiators. And the radiators have a chimney, so we get natural circulation of air to cool the radiators. So in the event of, say, a full station blackout where you lose all power, it drains, it goes to the drain tank, and then it cools in these radiators, and that lasts indefinitely, as long as until people can come around. It will keep cooling it indefinitely. So here's a picture of the expansion tank, the radiators, and the chimneys above it. Basement water is a closed system, so there's no radiation that's coming from that. We also have about 5,000 cubic meters of water in the basement, which means if somehow you manage to block all four of these chimneys, say with multiple aircrafts that hit it or a massive volcanic ash flaw, then you'll start boiling off the basement water, and that's good enough to last for about 60 days. It is at low pressure, so you can refill it with an ordinary garden hose. At Fukushima, one of the challenges they had was that their cooling water was at very high pressure, and even when they got water on site in fire trucks, the fire truck pump wasn't strong enough to be able to push water in to cool it. We're going to build a non-fission test platform as our first stage that will have a full-size can with everything inside of it as we plan to build it, and then a downsized secondary loop, and we'll just cool it to air. And the intent is to test as much as we possibly can before we get into having radioactive fission going on, before we're into a licensing regime and under the microscope. We expect that there are groups around in the world that very much hate nuclear and to try to find anything to make the public think that something awful almost happened. So we want to debug as much as we can before we get into that kind of close scrutiny by those organizations. So we will be able to use this to use electric heat to simulate the decay heat and show that we can remove the decay heat. We can use pressure to simulate to test the containment barriers. And we can time how long it takes to drop. We can run the pumps at full speed and check for vibrations. We can run it at temperature to check for thermal expansions. So we'll just get a lot of that engineering practice, first of a kind bugs taken care of in the non-fission test platform. That also means that we have less private money tied up. We haven't purchased the turbines and all the electrical gear, so that the investment during this time is lower, makes for better returns. Talked through most of that already. Once we're done with the non-fission test platform, we'll build a demonstration or experimental plant. That will be a full-size power plant, but we'll start out just by repeating the kind of tests we did at the non-fission test platform. Then we will go to subcritical, so no power, but be able to measure some neutronics responses. And then we'll go to basically zero power, and then step-by-step increase power slowly. So we will have, say, operate at 10 megawatts, but we have a cooling system that can handle 500 megawatts. And then that way we can safely confirm the expected behavior as we build up power and get step-by-step licensing from the regulator. One of the challenges with a molten salt reactor is it's a different kind, and almost all the regulations written in the world are written for light water reactors. So we have to work together with the regulator to both show them that our plant is safe, but also to train them and to train ourselves in how to safely regulate a molten salt reactor. Then we will, once we got it up and running, we will bring the politicians in and the press and have them watch when we cut all the power off. Fukushima, they had 45 minutes of cooling before they cut the power. We'll just cut it all off right away, and they'll see it's go to no power. We'll serve lunch, and an hour later, we'll see that nothing interesting is happening, and they'll eventually get bored and leave. And hopefully that will send the message, not just to the brain, but to the heart, that they really don't need to do a panic evacuation. And then we'll do the endurance testing and load following and much more. So total of about 2 years testing. One of the challenges is getting enough staff. For the US, we staff nuclear power plants by Navy nuclear engineers, people who've been trained in the Navy and are very disciplined. But if we're going to go to a worldwide fleet, we're not going to have that kind of pool to draw people from. And our reputation will hang on the worst run plant, not the best run plant. So that's why it's very important to us that the plant will automatically go to safe state and remain in a safe state without any operator actions. That makes it much easier to train the operators. Thank you, and questions?